Hi guys, welcome to Material Science lecture. Sorry that I had to cancel a class today. This is a replacement video for the lesson that you're supposed to have today, in which I will talk about the imperfection in crystalline solid. So far when we talk about crystal structure, I'm pretty sure everyone is imagining that every lattice point in the crystal structure will be filled with atoms. It's like, for example, the BCC crystal structure. So this has a 4-unit cell here. And you can imagine that this will fill up throughout the entire volume. So the perfect crystal will have atoms in each or motif in each of its lattice point, but that's far from true. There will be an imperfection in the crystalline solid. So we could expect with this million lattice point, there's probably a missing atoms or a plane that is not complete, or a stacking that is different. There's a stacking different between one grain to another. So those are all classified as the imperfection in crystalline solid. So in this lesson, we will look into or we will get acquaintance of all this imperfection. And sometimes, or most of the times, this imperfection inside this crystalline solid is not necessarily a bad thing. So here we will look into why is that, how we can manipulate the imperfection in solid to make the properties of the materials better. So let's get started. The learning outcome for this lesson is for you to be able to explain the types of defects arise in crystalline solid, for you to be able to explain how defects affect the material properties, and also to explain that defects are not necessarily undesirable. What is crystalline defect? So in a nutshell, it is a lattice irregularity. So instead of having crystal structure that has lattice point or motif in each of its lattice point, you probably have a missing atoms, for example. So it create a lattice irregularity or a crystalline defects. So it's basically just something that is not regular in that regular arrangement. So for example, you can see imperfection everywhere anyway. For example, this row of corn kernel here missing one point there. One of the kernels missing in between of these perfect or else a perfect corn row. So that's imperfection. So similar to that, crystalline structure can have imperfection as well. So there is no such thing as perfect crystal. So this defect can affect the properties of materials. So in this lesson, we will look into a little bit of this, and we will continue this discussion about how defects can be manipulated to strengthen the material's properties in our next module, module 4. So in this lesson, we will look into the 3 of crystalline solid, which is the point defects, line defects, and also the planar defects. What are the difference? What's classified as point defect? What is classified as line defect? And also what is classified as planar defects? For volume defects, we actually already covered this in module 3, lesson 1, in which we look into the shrinkage in ingot structure and also the porosity of the ingot. So that's shrinkage and porosity of the volume is considered as volume defects. Let's begin our discussion on point defects. All right, so what is point defect? So basically, in a nutshell, point defect is when we have missing point or irregularity on one or more lattice point in the crystal structure. So for example, if we have this crystal structure, perfect crystal structure like this, and then suddenly we have a missing atoms. So that is considered as point defect, and that point defect is what we call as vacancy. Or In another situation, we probably have a different atoms or the same atoms from the same host materials. Instead of sitting at its regular place in which it's supposed to sit there, instead of doing that, it sits at the space between the other atoms. So instead of occupying its own space, it goes to the interstitial space, and that is point defect. It causes irregularity in that crystal structure, and that's what we call as self-interstitial. Or, for example, we have impurity atoms. So instead of that host material sitting at that lattice point, we have another atoms that does not belong to this crystal structure. So it is an impurity atoms. So it sits at that lattice point of what's supposed to be the host materials. Instead, an impurity atoms sits there, and that is what we call as substitutional impurities. Or another example is that if we have instead a smaller atoms sitting in the interstitial of these host materials, that is what we call as interstitial impurity. One example I can give you is steel. So steel is an alloy of iron with carbon. So carbon atoms, if we compare to iron atoms, is very, very small. So it can reside at that interstitial space of iron metal. So that is interstitial impurities. So when the atoms is very small, it's small enough, the impurity atoms is small enough, it can sit at that point there. So this is the point defect that can exist in metal materials. So point defects can influence the mechanical properties of the materials. Why do I say that? So we take example again that steel, for example, if there's something, this impurity carbon residing in this interstitial spaces, instead of when we applied force that these atoms can now slide one on top of another, it will be harder for them to move, to slide one on top of another, because now we have impurity atoms residing at these interstitial spaces. So we actually, by alloying iron with carbon, we actually increase its mechanical behavior. We increase its yield strength and also tensile strength. So this strengthening mechanism we will cover in our next module, module 4, in which we will talk about the strengthening mechanism of several strengthening mechanism, how we can improve properties of metal. So those are the point defects for metal. And then we also have vacancy defects or point defects for ionic compound, which we will cover just briefly in this lesson here. So point defects basically is a dimensionless defect. Point defects such as vacancy provides a mean for these atoms to move around its crystal structure. So if you have a perfect crystal, atoms cannot basically move or diffuse from one point to another point. Only when we have vacancy that this atom, for example, can start moving here, and this atom can start moving there. So only with these impurities or with this imperfection that atoms can move around in their solid crystal. So let's talk about vacancy first. So if this is our lattice and we have one atom missing, so this is what we call as vacancy. So they are common, especially at high temperature when atoms are frequently and randomly change their position, leaving behind the empty lattice sites. So vacancy occurs naturally in all crystalline structure. So no such thing as perfect crystal. So the number of vacancy at equilibrium at any temperature in a crystalline can be determined using this equation here. So the QV here is the activation energy, which we determine through experiment. So if you are given this kind of question, you will be given this number here. And the K here is the Boltzmann constant. And we need to determine the number of possible sites. So the number of possible sites is, if this is a perfect crystal, how many atoms will be present in this crystal structure. So that is the number of possible sites, which we can determine using the formula of, let me write that down. So the number of possible sites can be determined using this equation. The density times Avogadro's number divided by the atomic mass. So that's how we find out what is this number of possible sites. So if it's perfect, what is the number of atoms inside this crystal structure? And to determine that, you use that equation there. When we have vacancy, what will happen is that we will put the atoms surrounding or neighboring the vacancy site under tension. So all the atoms around the vacancy will displace from the equilibrium position. So this will give rise of stress field in the vicinity of the vacancy. And also we will have a reduction in density. That is why when we learn about the theoretical density, I have mentioned that theoretical density will always be slightly higher than the real density, because the true density has some imperfection in the crystalline solid. So this is what will be caused by vacancy. And then also with a large number of vacancy, there can also be a reduction in ductility and also increase in hardness. So in most cases, diffusion can only occur because of vacancy. So vacancy are the most important kind of point defects because they accelerate all the process associated with displacement of atoms in diffusion. A self-interstitial atom is when a defect is caused by an extra atom, the same as the host atom, and that has crowded its way into the interstitial void in the crystal structure. So if this is our crystal structure, this is the original space or original lattice site of this host atom that you can see crowding itself in the interstitial space. So this is self-interstitial point defect. So this will also cause a distortion in the lattice structure, and therefore it will influence the mechanical properties of the material. Again, as you can see here, if you look at this plane here, if these atoms needs to slide, for example, so if you apply shear force here, these atoms on this plane here will start to want to slide. But because of this self-interstitial, it will be harder for it to slide over this interstitial atom. So naturally, it will increase the property, the strength of these materials. So that's one example how vacancy or impurities can improve mechanical properties of the material. Point defects can be in a form impurity as well. So there are two types of impurities, point defects impurities, which is substitutional impurities and also interstitial impurities. So due to the fundamental limitation of the materials purification method, materials are never 100% pure. So if we have an example of crystal structure like this, where the white color atoms is the host materials and the blue color is the impurity. So due to the crystallization, during the crystallization process, we would expect there will be some impurity atoms that are going to reside in the lattice point of the host material. So for example, I have this crystal structure here, and suddenly I have a missing atom not missing atom, impurity atom residing in that crystal structure. And that is what we call as substitutional impurity. It resides at the lattice point of the host materials. So substitutional impurity atoms is an atom with different type than the host atoms, but it resides in the lattice point of the host materials. So they usually will have the atom size that is similar or close to the host materials. So there are rules that needs to be fulfilled for the impurity atoms to be able to sit at that position of the lattice point, at the lattice point of the host materials. And let's have a look into that. So these rules are the rules that we call as Hume-Rothery rules. So let's go back to our lattice structure here, in which we have the impurity atoms as the blue color. The only way that this atom can sit in that lattice point of the host material if they have a size, it has a size that is no more than 15% the size of the host material. So that's the first rule that it needs to be fulfilled for that impurity atoms to actually replacing the host materials. Like for example, what I give you here. If the size is too big, it will not be able to sit in that position of the original host materials. So that's the first rule. And second rule is that it must have similar or the same valency. So it must have the same valence number of valence electron. And then it must also have the same crystal structure. So if the host materials exist as FCC, it also must have FCC. So that's the rules that must be fulfilled. And the last one is that it must have electronegativity that is comparable. So the two atoms that can be mixed together, no matter at how many percentage, is copper and nickel. So this is the example of when an impurity atom, no matter how many impurity atoms we have, it can always sit in that lattice point of the host materials. So if we have host materials as copper and we have nickel, nickel will always have a place in the crystal structure of copper. So the reason why is that when we look into its radius is not more than 15% in difference. And they both has the same valency and they have the same crystal structure. And the electronegativity is also comparable. So these are the four rules that must be complied or must be fulfilled in order for the substitutional atoms to reside in the host material's lattice point. Another type of impurity is the interstitial impurities. When the atoms that exist as impurities are very small, they can reside in the interstitial spaces. So that's why we call them as interstitial impurities. So it's reside at that space in between the host materials atom. So if we have, this is our perfect crystal structure, the impurities atom can reside in that interstitial space. So interstitial impurity fit into the open space between the host atom and the lattice structure. So that is interstitial impurities. And the example that impurity atoms that are really small and can fit into the crystal structure of a lot of metals is oxygen, carbon, nitrogen. They are small enough to fit in those spaces. For example, if we have BCC crystal structure, so this is a BCC crystal structure, impurity atom can reside in this tetrahedral position. So the white color one is where the atom can reside themselves. So for example, if we have that is the crystal structure of BCC, it can reside in that space there. in between the atoms. And for FCC, you can see that this is wrong. I have to correct this in your slide as well. So this is FCC. So for FCC instead, it can reside in the middle there. So for FCC, you can't see the space. It's actually right in the middle of this unit cell here. So as you can see that this space is very, very small. That is why only certain types of atoms, such as hydrogen, carbon, nitrogen, and oxygen, can reside in these spaces. So point defects such as vacancy can also happen in ionic compound or ceramic materials, and one of them is Schottky defect. So this is a defect found in ionic solid. So there are additional things that we need to consider when we talk about ionic compound. So if, for example, we have ionic compound here, sodium chloride, because there in ionic compound we have positively charged ion and also the negatively charged ion. In this case, we cannot simply have a vacancy of just one of these ions, because it will lead to charge imbalance. So in this case, when an ion missing, one cation also is going to be missing from the crystal structure. This is to balance the electrical neutrality of the compound. An equal number of anion and cation will be missing from the compound. So this is an example of sodium chloride, and this is a Schottky defect. Another example is when we have an ionic compound of magnesium chloride. So in this case, we will have two missing anion and also two missing cation to balance its neutrality. So due to this vacancy also, the density of the solid crystal will be lesser than the theoretical density of the materials. Point defect that can happen in ionic compound is Frankel defects. So in these defects, what happened is that the ion is not missing, or an ion or cation is not missing from the lattice structure. Instead, it squeezes itself into another anion placed somewhere else. So this is to also maintain its neutrality. So this defect forms when an atom or ion leaves its place in the lattice, creating a vacancy, but instead of going missing, it lodges itself in a nearby location, as what you can see in this example of an ion migration creating a vacancy in silver chloride. So not only an ion can migrate and lodge itself in a position somewhere else in the crystal structure, cation can also do that. So this is an illustration of cation migration, which will create a vacancy in a silver chloride. So the lattice contraction will happen due to the vacancy, leading to a decrease in density. That's about it for point defects. Now let's have a look at what is defined as line defects. The more common name that is used to represent line defects is dislocation. So this is a line defect within a crystal structure which contains an abrupt change in the arrangement of atoms. So dislocation can move. So it can move throughout the volume of the crystalline materials, and when force being applied, the mobility of these defects is what control the strength and the ductility of the materials, which we will look into further in our next lesson, so in our next module. In this module, we will just look at the type of dislocation. So there are two types of dislocation, which is edge dislocation and also screw dislocation. For edge dislocation defect, it can be easily visualized by an extra half plane on in a crystal lattice. So for example, I have this crystal structure here, and I have this extra plane squeeze in between the other planes, the perfect planes. So the edge of this extra half plane is what we call as edge dislocation line. So we will talk about how this can affect the mechanical properties in our next module. But just by looking at this crystal structure, what you can observe is that the lattice is going to be distorted. So by the presence of this extra half plane, the lattice will be having a distortion. So the magnitude and the direction of the lattice distortion resulting from this dislocation in the crystal structure is what we call as Burger's factor. So what is Burger's factor? How do we determine the Burger's factor? So it is not the burger you eat in McDonald's, okay? So the Burger's factor can be determined by comparing the perfect crystal to the distorted crystal. So if you just focus your attention to this corner here. So this corner is a perfect crystal. There are no additional half plane here. So if you look at this perfect crystal, if I go one position to the x from this origin to the positive x direction, 1 point to the negative y, 1 point to the negative x, and 1 point to the positive y, it will close that loop. So it will go back to that origin. However, let's have a look if we have one half extra plane. If let's say I move 4 position in the x, positive x, I'll just do 1, 2 first, and then 4 position in negative y, 1, 2, 3, 4. Another 4 in the negative x, 1, 2, 3, 4, and another 4 in the positive y, 1, 2, 3, 4. And I still owe 2 in the positive y, a positive x direction. So I'll have 1, 2. So as you can see, it does not close that loop. So the factor that is completing that loop is what we call as Burger's factor. So the Burger's factor associated with the dislocation is a measure of the lattice distortion caused by the presence of this line defect. So the magnitude and direction of the slip, later when we talk about slip plane, is going to be represented by the Burger's factor. So when we have dislocation in a crystal structure, when we apply force, external force, it will start to move. So this is what a control mechanical behavior of the materials. Edge dislocation or dislocation is the defect that control if the material is going to be ductile or it's going to be harder or brittle. The way dislocation moves is, if you want to imagine, is the same way as when we are trying to straighten a carpet. So if you imagine that I have this carpet here that I want to straighten to the corner of the wall. So normally the easiest way for it to move is by creating these small ripples. So that ripples represent the dislocation. And each time I kick it, it will move a step. And I kick it again, it will move a step until eventually it will get to that corner. So that's what happened during the movement of dislocation. So as you can see here, if I mark it, this is my edge dislocation. So this is my edge dislocation. So when we apply an external force, here we apply shear force, what's going to happen is that because in this edge dislocation, the atom at that H dislocation did not have any bonding with atoms at the bottom of it. So what's going to happen when we apply an external force? This will break, these atoms will break, and the H dislocation, atoms at that H dislocation will now form a bond with this one. All of these atoms will form this one. So that's how it moves. It moves by a constant consecutive bond breakage within the crystal structure. So dislocation motion occurs by consecutive bond breakage. So if you can see here again, now you can see that H dislocation that was here before now move to this point. And if we keep on applying that force, that shear force, this will keep moving. The next plane will break, the bond between that atoms in the next plane will break, and it will bind with these H dislocation atoms. So that H dislocation is now going to move to the front until the end, when it reaches the edge of the volume of that materials, where it will create what we call as a unit step of slip. So in the end, dislocation movement is what causes plastic deformation, is what causes the materials change in its shape. When we perform forming process, forging and all that, this all involve the movement of dislocation. Type of dislocation or the line defects is screw dislocation. So instead of having extra half plane in the crystal structure, the lattice itself is sheared. So the blue line that you can see in this, the dark blue line, is the direction of the screw dislocation. So as you can see here, one side of this crystal structure is higher than the other one. So the other one is lower. And if you focus your attention to the light blue color, you will see that this line here is look like a spiral shapes that look like kind of like a screw. So the motion of dislocation follows this helical path of the screw. That's why we call them as a screw dislocation. So just by observing this crystal structure here, you can see that this dislocation also is going to distort the lattice structure, and they also can move, and this dislocation motion will cause plastic deformation in the material. And that's about it for line defects, and the final one we will discuss today is planar defects. So this is a two-dimension defects. So planar defects are boundaries that have two dimensions and normally separate regions of the grain. A planar defect is a discontinuity in the perfect crystal structure across a plane. So a grain boundary is considered as planar defects. So when we learn about solidification, if we have one seed starts to getting bigger, another seed starts to getting bigger as well during the nucleation and the growth. So when they starts to impede each other, the region where they impede each other is a planar defects, and that region is what we call as grain boundaries. And also we could have phase boundary, in which two materials that cannot dissolve in each other. What will happen when they solidify is they will create two phase. So that phase, one phase to another, the region where they meet is also a planar defects. And lastly, if we have a stacking fault. So if we have, like, let's say, like when we talk about stacking sequence, we have for FCC, we have A, B, C, A, B, C. But suddenly we have A, B, C, A, B, C. So the region where we have that stacking fault is going to be a planar defects as well. So grain boundaries is a region that's separating the two small grain or crystal having different crystallographic orientation. They will exist in polycrystalline materials. So this is the crystal schematic representation of the grain boundary, in which when we learn about solidification, we know that when nucleus starts to nucleate in the molten metal, all the atoms start to attach themselves to that nucleus. And we probably have hundreds of thousands of these nucleus, and they're all going to grow bigger and bigger. When they start to impede each other, the region where they impede each other, the area is a two-dimensional area, and this area is the grain boundary. In our module 4, you will see how we can manipulate this area to increase the number of grain boundaries. The grain boundaries area can actually strengthen the mechanical behavior of the materials. Also, for grain boundaries, this is the region where the decrease in electrical and thermal conductivity of materials will happen, and also this is the area where corrosion will initially starts to happen. Another planar defect is phase boundary. So a phase may be an accumulation of alloying element in the host lattice material. So for example, if we have like for instance steel, so steel is iron with carbon. Carbon inside the iron, if there's a huge percentage of it, it can also bind with itself. So it will bind with itself to create graphite, and this will exist in the volume of that steel. So that will create a different phase compared to the iron itself. So the region where they meet, the graphite and the iron, is a planar defects. So this is a phase boundary. So it is between the two phase, which is the iron phase and also the graphite phase. In materials such as cast iron, we have a lot of graphite inside these materials, and the region where graphite and the iron meet is the phase boundary. This is the schematic representation of phase boundary, in which we have two different atoms creating their own phase inside a bulk materials. So this is phase 1 with phase 2, and in between them, or the region where they meet, is what we call as phase boundary. So this boundary is formed due to the immiscibility of one phase with the other on the side of the boundary. And lastly, we have stacking fault. So this planar defect form when there is a disordering of crystallographic plane. So the stacking fault is any defect that alter the periodic sequence of layer. So all crystal whose structure can be described as layers are prone for stacking fault. So for example, when we learn about stacking a sequence of HCP and FCC, we learn that they have different stacking sequence. So for HCP, it has A, B, A, B, A, B. For FCC, we have A, B, C, A, B, C. But it can happen during the solidification of the materials that this stacking sequence can be disrupted. So instead of having A, B for HCP, we have A, B, A, B, A, B. We suddenly have A, B, C, A, B, A, B, A, B. So the region where that stacking fault happen is a planar defects. So basically this region of planar defects where two phases meet each other, or stacking sequence happen, or stacking fault happen, or grain boundary happen, are filled with atoms with unfulfilled valency, and making them have a very high energy. Therefore, a chemical reaction usually will start in this region. So chemical reaction like corrosion or diffusion will start in this region. So that's basically it for the different types of crystal defects. So in summary, we have learned there are 4 types of defects, which is point defects. This is a dimensionless defects in which we will have a missing point in our lattice structure, or we have a lattice point that has been replaced by impurity. So that is a dimensionless defects. And another type of defects is the one-dimensional defects, which is line defects, and it can be categorized as it can be either edge dislocation, in which we will have extra plane, or a screw dislocation, in which we have a lattice structure that is sheared. Or another type is planar defects. This is 2-dimensional defects, in which the area where atoms has unfulfilled valency. And the volume defects is a 3-dimensional defects, which we have learned in our previous lesson. This can be either a shrinkage that happened during solidification or a porosity. So these defects can affect the properties of the material in terms of the strength and ductility, as well as other properties such as electrical properties, chemical properties, and their degradation properties. And these are not always bad effects. So that's about it for today. I will continue with the second video where I will talk about diffusions. Thank you for listening.